We are recording, I think.
We are.
Sweet.
And I'm not leaving. I'm always tempted. One of these times I'm just gonna be leaving.
You're just gonna leave, and I'm like, okay, let's start, and then you'll come back.
Mm-hmm, mm-hmm.
All right. We've been waiting all year for this. Every year, there's like a group of students at the beginning of the year. They're like, when are we gonna learn this topic? And I'm like, at the end of the year, you have to wait 9 months for it. 8 months, I guess. And we are here.
Huzzah.
Huzzah. Today's lesson
is complicated.
Hopefully it's not. Hopefully, after you proceed through this, it's pretty straightforward. But we're introducing the next level of numbers. Remember that thing we did like in September where we talked about the natural numbers and we defined them all, and there was like arguments about is 0 an integer and stuff like that. I guess 0 is an integer, but like is 0 natural? Like is the natural number 0 plus or 1? We talked about natural numbers. We talked about rational numbers, integers, rational numbers, real numbers, and we are now adding a layer, like from Shrek, and a layer of an onion to the mix.
Or a parfait or a cake.
Or a cake. That's what Donkey says. All right. But to get to there, let's like remind ourselves how far we've come from childhood.
Mm-hmm.
Right. I want you to put your shoes in first grade, Mrs. Contreras.
Okay. My shoes were like, they were the sneakers with the Velcro because I didn't like tying them, and then they had the blinky lights.
And if you like, yeah, I was gonna say, if you smash the foot, does it like blink? All right. All right. So I want you to put yourself in the shoes of first grade Mrs. Contreras, but I also want you to like kind of superimpose a Mrs. Contreras that knows what square rooting is.
Okay, that's fair.
Right. So you know what square rooting is, but if I said to first grade you, what is the square root of x squared? What is the solutions to the equation x squared equals 9? What would you say?
I would just say 3.
3.
Yeah.
Whoa. And I am sharing.
My brother, he did teach me about multiplication when I was like in kindergarten, so I probably might have known that.
Yeah.
In first grade.
And that is what the question is. What times itself equals 3? We're going to be saying that sentence to ourselves over and over and over again over the next 3 lessons. What times itself equals 9? 3 times 3 is equal to 9. Right? Mm-hmm. Why did you say 3 and not like any other numbers?
Because at that point, my number line only went up. Right. It didn't extend in the negative direction. My mental number line, I guess.
It like consisted of the countable numbers. That's what you were doing for. You were counting. You know, I know I was like sitting on the carpet with like objects and moving them around. Maybe I don't know. Anyways, fast forward a little bit in your life. We get to 5th grade.
Okay.
And actually, this is a little.
Year.
What?
That was a cicada year.
That was a cicada year. Cicada year for me was, I think, 4th grade, because I believe you're a year older than me. But for you, it was okay. Okay, so imagine all the cicadas. Now stop imagining all the cicadas because this has nothing to do with that. If I ask you the same question, what times itself equals 9? What would you say?
I'd probably say 3 and negative 3.
3 and
I was aware of integers.
Yeah, and actually, I think I distinctly remember. I have this weird. I wouldn't say weird. I have this distinct memory of learning about negative numbers in 6th grade. I don't know like where that is compared to the average person, but I remember negative numbers in 6th grade. I don't know why, but I do.
It also depends on what average you're taking. Like, are you taking average of all the people of all of humanity? Because then like it's pretty dang advanced.
It's true. That's true.
Keep it in perspective, Mr. Bird.
That's true.
You do great.
Thanks for keeping me level-minded. Okay, so we have 3 and negative 3. So what happened between 1st and 5th grade?
We learned about negative numbers existing.
But like, think about 1st grade self. Like, why didn't you know about negative numbers in 1st grade?
Because I think we didn't need to bother with it. We were still learning about how to put things together, like moving things around on a carpet, like you were saying. So we were looking at physical objects that we could manipulate and representing those in different ways and grouping them together, but not necessarily doing things where we're taking away more than what we had.
And that actually answers my next question was, what kind of necessitated the need for a negative number? Why did you have to expand your mind that way?
Well,
But
we
you
need
kinda
to
answered
think
that.
about beyond just like things that were physically manipulatable.
So
But
we're
we're
like,
still thinking about distinct, like countable things.
I think that's one of the cool things about humanity too, is like we have these things that are physical, countable things, but then we are able to, in our brains, conceptualize the idea of not just the absence of things, zero, but like, I don't know, I can't even put it into words. It's like, I don't know, crazy to me, even though it doesn't feel that crazy. I don't know. Anyways,
We can imagine beyond what we see.
yeah, exactly. I think that's a really cool thing about humans. Oh, and I bet you some animals, other animals can do it, but I don't know. I bet you there's some science experiments out there that have like established that dogs can do the same thing. I don't know.
I think there is like there was a study where like bumblebees could do math somehow.
Yeah. I don't know. But that just like really like blows my mind. Let's move on.
Okay.
This is the sound of growing up. We get to 7th grade. And I ask you, hey, what times itself gives you 5?
Oh, and then I can answer that because now I have like the gaps between our numbers. I can think about what those are. And in a way that's beyond fractions, beyond things that we can just represent as a number over a number. And so we know that that's irrational, right? That's somewhere between 2 and 3. Because 5 is between 4 and 9. I think we've talked about that before.
Yeah. It's like the trick to figuring out. Yeah.
But also whatever that something is, but the negative, the opposite of it.
Yeah. And then what symbol do we use for this?
The square root.
The square root symbol. So the square root of 5 and the negative of the square root of 5. I think this is even more.
Plinus root 5.
Plinus. Yeah, people have been using that in class and it warms my soul. But what was I going to say? I think that's even more crazy than negative numbers is the concept of an irrational number. Like, can't even, like, what? How do you have root 5 of something?
You sound very Pythagorean, Mr. Hood.
I know, yeah. Very exactly. This drove people insane that the fact that this number can exist, a number between 2 and 3. Well, there's lots of numbers between 2 and 3. Maybe I should have put in like 3rd grade a rational version of all this, but whatever. We have the natural numbers, we have the rationals, we have the integers. I guess the rational will go in between 5th and 7th, but then we got root 5 and negative root 5. Cool. But the important thing to note here is that in 1st grade, you didn't know about negative and irrational numbers. You didn't know about them. And then in 5th grade, you didn't know about irrational numbers. So like, what's to stop you from in 7th grade not knowing about other things that are new? So now we are here in high school. And we have the question, what times itself gives us negative 9? Do you know what times itself gives us negative 9?
I think we should maybe use something like make something that is the square root of negative 1 and then use that along with all the math we knew from before.
Well, let's do this. Let's do this instead. Let's define something that when you square it gives us negative 1. I think that'll solve our problem. This number is a number that when you square, you get negative 1. All right, keep that in mind. A number that when you square it, you get negative 1. So what then will give us negative 9?
If we have 3 and this I thing.
Okay.
And if we have negative 3 and this I thing.
Or x equals negative 3 in this I thing. Let's double check. All right, this is our definition here. So 3i times 3i. Let's allow the the what's it called? Commutativity of multiplication. Yeah, thank you. Let's allow that to exist here. Move some stuff around. 3 times 3 times I. We get 3 squared. We get I squared. I keep doing some really bad notation here.
Okay.
And then we get 9 times -1, -9. And it'll work with the other one too, because -3 times -3 is also 9.
Yep.
I'm going to erase this work. But let's open our minds. Let's expand our understanding of the numbers to just, let's define something that when it is squared gives us the number -1 to address this situation. Right? Let's say we want solutions to the equation x squared plus 9 is equal to 0. Let's invent an answer to it. Just like we invented an answer to this. Just like we invented an answer to this. I think the only one of these that's intuitively makes sense is the first one. Anyways, before we proceed, we have this new number I. Its property is that when you square it, you get -1. Let's look at all of the numbers that we do have. So what was like the first fundamental thing that we learned about numbers in first grade?
The counting ones, the natural numbers.
The natural numbers. Okay. And what is in this set?
1, 2, 3, 7,
7.
12, 5, 8, 13, 21.
Is 0 in the set? Let's not go down that road. After the natural numbers, what was the next number that was taught? Or
Well,
was
we're talking about the opposites of those. So
Mhm.
the negatives, all of those, which we call those the integers.
the integers? Cool.
Which is funny because we just took the end and flipped it over.
But the part that's been bolded is different. What goes in this set?
Actually, Mr. Kirk, I built the middle part of my natural numbers.
Do you really?
Yeah,
No, you don't.
I actually do.
Do you really? Awesome.
Yeah.
Okay, cool. Can you write that on the side there for me? I need to see what this looks like.
I just like a double.
Oh, I kind of like that actually. That's pretty good.
But, you
That
know,
looks like the symbol for Northwestern. You also did it in purple, which is Northwestern Scholars. Anyways, what are some numbers that are in the integers?
-1, -2, -3, -5, -7, -12, and also +1, 2, 3,
Yeah.
5, 7, 12.
And I appreciate that you said that because notice that our natural numbers are within our integers. I really want to fix this and do what you did, to be honest.
Okay.
Anyways, yeah, our natural numbers are within our integers. What did we learn next?
We learned about rational numbers, where we were taking a ratio of our integers. So you could have like 1/2, you could have 3/7, negatives of those. You could make the numerator bigger, so like 12/5. It's totally fine. Yep, 7/4.
Minus 12/5.
Minus.
Okay, so we got the rationals. Sweet. Right? Notice that the natural numbers and the integers are both within the rationals. -2, 2, 1, 12. These are all rational numbers. What was the next thing we learned?
We learned about irrational numbers.
Rational numbers, which I'm going to call the real numbers. And what kind of numbers fall into this category?
Things that we can't represent as ratios of integers, but still are not including square roots of negatives.
True.
So like square root of 5, or square root of 2, or pi, or e,
Or negative e.
or negative e.
Plinus e.
Wow, minus e squared.
Oh my gosh, I'm gonna do it. I'm
What
gonna
do
write
you
it
think
down.
is bigger, e to the pi or pi? To
I
the
saw that the math department's Instagram posted that, and I actually thought about it for a while. That was a really funny post. I like everyone check out the math department's Instagram. What is it? At what?
Blair Math Rocks.
Blair Math Rocks. Any underscores or anything like that?
Nope, just Blair Math
Blair Math.
Rocks.
Okay, sweet. I'm gonna check it out. There's some great memes that go up there. Anyways, meet the real numbers. And now here we are. We started with the counting numbers. Kind of made sense. We introduced some negative numbers, which to me still baffles me. Then we're like, okay, rational numbers make more sense than the negative numbers to me for some reason. Can't explain why. Square root of 5 makes no sense to me. And here are a new set of numbers called the complex numbers that exist. And you know, I'm still to this day, I'm trying to wrap my head around it.
It's okay.
But they do math. And they help us understand much more complicated things. And we have this new number I. What number do we have above this?
2i?
2i. I was going to reference the 3i up here.
Oh, okay.
Yeah.
Negative 3i.
Negative minus 3i.
Oh.
Watch this. And this will make more sense later, but we have 1 plus 2i. So all of these are called complex numbers. And this has a real part. And this I is used because it's called an imaginary number. It's not really imaginary. It's certainly real. It exists. It helps us solve math. But this is called the real part. This is called the imaginary part. But we can have the combination of two numbers. Why this makes...
You said that I was certainly real, and I don't want to confuse our students.
Yeah.
I is not in the real number system.
Yeah.
It's outside the real number system.
Yes. And there are more stuff. Thank you for clarifying that. There are larger sets. The complex numbers, the real numbers, all these things are subsets of even larger sets of numbers. I don't know much about them, but you can look them up.
There's really cool number file video about it.
Yeah. Do you remember what they're called? So people can look it up easier.
About like non-algebraic or something.
Yeah, I can't remember.
Watch the number file video. Get back to us.
All right. Let's take this and run though. Let's try to think about what this number I actually means. Okay. So I'm gonna get myself a number line here. I'm gonna add 0 to it. And actually, let me do this just to really like drive home the point that this is all new. Here's a number line. Here's that first grade number line. Right? What went right at the beginning of our first grade number line?
1, because that was like the first day of school, right? That was when we started.
True. Can I put 0 there just for all intents and purposes?
Sure.
I'm gonna put a 0 there. Right. And then what could you do? What else is on your number line? 1. Right?
1, 2, 3, 4.
Cool.
500.
And I'm gonna go ahead and stop there. And then now we are in 5th grade. What do we add?
We got some integers. So we got like -1. Whoa. Mr. Kirk's getting fancy.
Getting fancy. Ooh, let's go back to that. So we added -1, -2, -3. Is that what you said?
Mm-hmm.
Sweet. So -1, -2, -3. Cool. And then we added rational numbers, the numbers in between. And then we added the irrational numbers, the number in between those. And we have now the real number line. But let's talk about what it means to multiply. Let's say I have the number 2. If I multiply the number 2 by 3, what do I get?
6.
6. 4, 5, 6. If I multiply the number 2 by the number 3, I get the number 6. Do you know what's happening geometrically on the number line when you multiply a number by another number?
Is it like the skip counting thing?
Kind of. Yeah. Well, I'm going to take this to geometry real quick. If I take a triangle and a center of dilation, and I dilate this triangle by a scale factor of 2, what I do is I take the distance between the center and each of the points, and I scale it by 2. I get twice as far away. I get A prime. I get about right there. C prime. Not C prime, sorry. Let's call that B prime. We'll call this, I already used the letter C. Let's call this D. I get right about there. I get D prime. What have I done to my triangle?
You multiplied, right? You like made the area bigger.
Yeah.
By a scale factor.
I think I made the area bigger by a scale factor of 4 because it grows with the square. But I essentially have a triangle twice as big, right? When you multiply a triangle by a number 2, what you're doing is you're dilating it. You're scaling it by the scale factor 2. I've been grabbed. I love it. Okay. So when I'm on the number line, I have a one-dimensional triangle in a way. when I multiply the number 2 by 3, I am dilating its distance from the center by 3. I had a distance of 2, and those are the worst curly brackets ever made, but I have dilated my distance by 2. What happens if I multiply by -1?
We go in the opposite direction. So we dilate the same. We dilate like 0, but we go in the opposite way.
We dilate by 1 actually,
1.
right? Yeah. Well, actually, let me change this. Let me change this to like a -2. What do I do? What does that do?
So we go dilate by factor 2, and in the opposite direction. So we get
And then in the opposite direction, so we get to -4. Right? So we dilate and we kind of move through. But I'm going to do the triangle real quick. I go in the opposite direction too. It's going to be like down here. I'm going to move the B in the opposite direction too. It's going to be like right there. Sorry, it's kind of overlapping. And then I'm going to be like over here. What happened to my triangle this time?
got flipped.
Got flipped. And how do I get from this triangle that I've starred to this triangle right here? Let me do this. A prime, B prime, D prime. How do I get from this triangle right here to this triangle right here? Think about like a rigid transformation that will get me there.
Do we reflect?
Not reflect, because if I reflect it over like some line, A would be on top, B would be here, D would be here. And I would have a triangle in like the same orientation as A, B, and D.
So then we need to rotate?
Rotate. Right, so that's where I was going. When you dilate a triangle by a scale factor of -2, you grow 2 and you rotate 180 degrees.
Or pi radians.
Or pi radians, yeah. So I'm going to go ahead and get rid of all these triangles now, but I want you to keep that in your brain. I'm just only getting rid of them so that we have the space. Let me do this. Commie magic. Cool. So we got -2, right? We dilate -4. We dilated 2 and we rotated 180 degrees. Right? So that's the thing. What does -1 do? What is -1's function on the number line?
So in that sense, I guess we rotate.
How and how
180
much?
degrees.
180 degrees.
Or pi radians.
Or pi radians. Right, so what's true about I and -1?
Is there a rotation that happens then?
Okay.
So
What's the
then
relationship between I and 1? I and -1?
I is the square root of -1, or I squared equals 1.
Yeah. So what do you think it means to multiply by I?
That means that we rotate, instead of a whole 180 degrees, we rotate only halfway there, which is 90 degrees. Or
so 1, or let's do 2. 2 times I, that's going to be 2I. But where is it on my picture?
So we go over to 2, and then we rotate up to the vertical, like perpendicular to the number line that we have now.
Why is that just that 2 coming?
I don't know. Oh, because you drew it probably at the same time.
Yeah. Commie, and it's not perfect. It's good. It's not the best. Oh, it's the best. It's not good. It's not perfect. All right. Let me go ahead and add a new dimension to our number line.
Whoa.
Let me do that. And then like pick another point and do that. Pick another point and do that. All right, so
extra.
We are dilating by magnitude none, but we're rotating 2I is right there on the number line.
Mm-hmm.
And what happens if I multiply by 2I twice?
If you multiply by 2I twice, then we get 4I squared, which is -4.
So multiplying by 2i twice does the same thing as multiplying by -4. So the function of the number I now has a geometric meaning. Multiplying by I takes a number on the number line and rotates it on the number line out of the number line into what we call the complex plane. This is our real number line, and this is our imaginary number line. So I talked about some other weird numbers up here. 1 plus 2i. What do you think the number 1 plus 2i is? That is its real component and its imaginary component combined. What do you think that number does? Multiplying by that number geometrically.
Would we go on the real axis, no dilation, but then in our, will we go around in the perpendicular plane?
Well, I see, and I think I see why you're saying that. Are you saying that because the real part is causing no dilation?
Mm-hmm.
But don't forget that 2 also causes a dilation.
Mm.
Right. What this number does is it dilates that much. And it rotates this much.
So then can we connect it to all that other stuff that we've been doing with
All
like
that.
everything with distances and angles
And polar stuff and stuff like that? Absolutely. And we're going to do that, not today. But this is the complex plane. And all of these new numbers, 2i, I, 1 plus 2i, -3, -3i, where would that be? That'd be down here. They all exist. Yeah.
Because you're going to the -3 and then you're doing another I.
Mm-hmm. Well, so -3 plus minus I would be like right here.
Mm-hmm.
But we now have expanded. So we started with just a number line going in the right direction. Then we added a number line going in the left direction. Then we filled in that number line over the years. And then now we are leaving our one-dimensional sense of numbers and entering a second dimension. And then in doing that, we're getting like a lot more numbers. We're getting a whole plane of numbers. So this is the complex plane as opposed to the real number line. This is the complex number plane. All right, let's keep going a little bit. Let's understand this a little bit more. Evaluate the following. I, that's just I. But what is I squared?
-1.
-1. And I want you to think about this in terms of rotations. What is I cubed?
-I.
-I. But you could also do like I squared times I. -1 times I. -I. If you rotate 4 times around the complex plane, what do you get?
1.
1. If you rotate 5 times?
I.
6?
I to the 4th times I. 6 is -I.
-I?
-1.
-1, yep. 7?
-I.
-I. And 8?
1.
Back to 1.
Wait, there's a pattern.
Hopefully you noticed a pattern. What is it?
Oh, there's a really cute song chant thing.
Is there really?
Mrs. Wheatley does.
What is it really? I need to know it. We need to get Miss Wheatley in one of these videos.
So it's I won, losers in the middle. Because the negatives are in the middle.
Wait, I won, losers in the middle?
So right, I won. No. Oh my gosh.
I'm just writing what I'm hearing.
I won.
So
won.
I won.
Uh-huh.
Okay, I won.
I won. And then losers in the middle.
But what does the losers in the middle mean? Okay. Oh, and that's like
and that's the pattern.
I see it. I won. Losers in the middle. I don't know if I like to think of negative numbers as losers, but all right.
Yeah, but you know.
It is. It helps. Boom. I really like this rotation thing though. I didn't learn this until recently, but I really makes me feel happy.
It's
2i.
really cool.
Yeah, I think it's super duper cool. What is I to the 117?
Okay, wait. So I to the 100 is going to be 1.
Mm-hmm.
Right. Okay. And then so let me write stuff down. So we have oh, you got it? Okay, got it. So
What's
and
left
then
over?
we have I to the 16, right? And that's also gonna be 1. So then we just have
Mhm.
another I left. So it's 1 times 1 times I, which is just I.
Oh, nice. How about 412?
I think that's divisible by 4.
I think so, right?
So then are we at 1?
Yeah, we're just back at 1. Yeah.
Bet.
So hopefully, it's pattern. It's the 4 divisibility pattern, whatever that is. Find the closest number that is divisible by 4, and then work your way towards it. For you, that was 116, and boom, you got to I. Second one, you knew that it was divisible by 4. Boom. I think people get worried when there's complex numbers, but really it's just rotations. I'm like spinning in my head. Anyways, here's a few things about complex numbers that are worth noting. Do you want to read it?
The complex number a plus bi, where a and b are real numbers, is said to be in rectangular form. That makes sense, right? Because we were drawing things in a rectangular kind of coordinate-ish.
Yeah.
A is called the real part, and b is called the imaginary part. If b is 0, then the complex number is a real number, because we're getting like a projection onto the real axis. If b is not equal to 0, then the complex number is an imaginary number. And if a equals 0 and b is not equal to 0, then the complex number is a pure imaginary number, because we're getting a projection onto the vertical axis.
So these are like the 3 scenarios that are happening there. Yeah. If it's on the real number line, it's real. If it's on the imaginary number line, it's imaginary. And if it exists in the plane elsewhere, it's imaginary. Purely imaginary. Right? All of these numbers are complex. The vocabulary is a little bit weird. I don't mean to be confusing. I'm sorry that I was earlier. I think as we use it more, we become more fluent with it.
But also, I think it varies from like what you're talking, like who you're talking to. Because I feel like similar to like all this like whole number thing or whatever, like I don't think imaginary was a distinction from like complex in my like when I had learned things.
Yeah.
So it kind of like varies based on who you're talking to.
Yeah, I hear what you're
But
saying
as long
now.
as
Yeah.
you like establish what you're talking about in the beginning, which is why preambles are important.
Let's start a complex number club. We can have a
Well, there's a whole,
constitution and a preamble.
There's like a whole class on complex stuff.
It's true. Complex. That's true. I feel like that's what we should go with ultimately. But anyways, let's keep going. So we have operations on complex numbers. And guess what?
It's totally different from everything we learned before.
It's totally the same as everything we've learned before. Vectors, polar, like boom, boom, boom. If you want to add -3 plus 5i plus 2 minus 4i, add it like vectors. You're going to add the real part. You're going to add the imaginary part. And later on, we'll learn that that is consistent with this new geometry. Multiplying by -3 plus 5i, you're rotating the angle that makes with the positive x-axis, and you're dilating by the magnitude of that thing, which is its length from the real complex origin. I'm going off on a tangent. This is exactly how we've done it. What is -3 plus 5i plus 2 minus 4i?
-1 plus I.
Plus I. And we can put the parentheses. We don't have to, but the parentheses are there just so we're coupling the imaginary numbers, the complex numbers. Wow, it is really easy to mess up this vocabulary. Mm-hmm. How about subtraction?
So we have like -5 plus 9i.
Plus 9i. Boom. 5 minus -4i. Sweet. Ooh, multiplication.
So you might feel like the urge to FOIL, and you're correct.
Because everything is just like, these numbers work just like we've always done. Negative 3 plus 5i, 2 minus 4i. What do we get? Negative 6 plus 10i. So I've done this. I've done this. Now let's do.
Wait, you're not foiling, Mr. Kirk.
I am wait, I don't know. No, yeah, I am. First,
Outer.
inner, outer, last. I was fioling.
Yeah.
Fine. I will foil. I will foil for you.
Because I said foil.
I know.
That's
I know.
the only thing.
And then
What
inner
numbers are you
plus,
saying? It's 12.
and then last.
Mm-hmm.
What is that going to be? Negative 20 I squared.
But I squared is negative 1, so plus 20.
I had a teacher. So for me, and talking about like how to remember stuff, I had a teacher in, I think it was 9th grade, who taught me complex numbers, and they liked the Backstreet Boys. And I don't know if this is a Backstreet Boys song, but she would always sing, I squared is equal to negative 1. And that's been stuck in my head. Not stuck in my head, but it's like in the back of my brain since 9th grade. So if anyone can figure out what Backstreet Boys song that is, that might like put to rest this thing in the back of my brain.
Or it's just one of those brain worms that's just in your head forever.
That's true, yeah. What do we got here? 14 plus 22i is what I got. Good stuff. How about division?
Well, we can't just like straight divide like negative 3 over 2 and like 5i over negative 4i. Like that feels like cheating.
We are following the rules that we've always known. Do you remember how we simplified fractions way back in September?
Oh my gosh, no. We did get a super denominator killer.
No super denominator killer here. That's what we would do if we had mixed fractions, where we had a fraction with fractions all over the place. Fractions in the numerator, fractions in the denominator. Think like, I think we've used this in we used it in the quadratics unit. We definitely used it in the trig unit. We used it, I don't know if we used it in the triangle and vector unit. Maybe we did. We definitely use it in the derivation for trig stuff unit. How do I simplify this? Involves something that you learn in like Spanish or French or Latin.
Conjugate.
Conjugate. What's the conjugate of the denominator here?
2 plus 4i. So we're like effectively like trying to cancel out the I in the denominator.
So, yeah, we're like realizing the denominator. Instead of rationalizing it, we're realizing it. I don't know if I've ever said, I feel like I say that every year and I forget and I laugh again the next year, but we're realizing this thing. It is pretty great. So we know how to do the top. So we got negative 6. I'll do this for you. Foil. Negative 12i.
Wait, it's the same as on the other side? No, it's not.
It's not. It's not.
That would have been good worksheet design, Mr.
Bird. But this is not good worksheet design.
Right.
So 2 times 2 is 4. The negative 4i and the negative 8i and the positive 8i are going to cancel. We're going to get a negative 16i squared.
Which is 20.
Which is 20. Positive 20. So 4 plus 20, 24 in the denominator. We have realized our denominator. And then on top, we get negative 20 here.
So negative 26 minus.
That's our real part.
20. No, minus 2.
Excuse me. Minus 2i. And then
by 2.
What is that going to be? Negative 13 divided by 12 minus 1/12i. I think I got that right. Boom. That's our real part. That's our imaginary part. And that is our complex number. All right. We're almost done with this video. We got a few more things to touch on. But let's use these complex numbers in reality. Let's say there's a scenario that involves solving a quadratic equation. Let's try to solve this. What do you want to do?
Quadratic formula, x equals -7, -7 minus the square root of, what's that, 49
49, yeah. Minus.
minus 4 times 15. What's that?
Yeah, 4 times 1 times 15, that's 60.
60.
Oh.
Oh,
Ooh.
don't complain. It's gonna be fine.
Oh. No, but I'm saying, like not 4 months ago, we would have been looked at that and be like, no solutions. But we have expanded our mind today in a way that has happened several times in our lives. This is just one of those moments where it's happening. 7 halves minus some
It's negative
complex
11.
number. Negative 11. Okay. So how do we simplify this thing?
Well, can we take this root negative 11 and like translate it?
Well, can you rewrite that negative 11 as 11 times I squared?
So
Like, do you see what I'm saying?
like that. Boom.
Yeah. Do you know why I wanted to do that?
Yeah, because we have a square root and we have something squared, so we can
Yeah.
So yeah,
Do we need to put an absolute value around that I squared? I don't think so.
I don't think so.
I guess we could, but the absolute value of I guess, is I. What's the absolute value of a complex number? Journal idea. I've never heard of this before. The absolute value of a complex number. I don't know. I guess we use the absolute value bars. We're going to literally on the next page, we use the absolute value bars to signify magnitude. We'll talk about that in a second. So maybe not. Maybe we shouldn't put absolute value bars around that. Should we verify that that solution works?
Leave that as an exercise for the viewer.
Okay. It is an exercise. It's equivalent to maybe running 10 miles.
Wow.
Just kidding.
Quite the exercise.
It would take me the same time to run 10 miles as to plug that back in. That's not true at all. I definitely encourage everyone to take these numbers. Just do one of them. 7 plus I root 11 over 2. Plug it into here. Square it. We just talked about how to square numbers. Right? FOIL. Plug that thing in. Square it. Subtract 7 of it. Add 15. And you should get 0. Because when you square that I, the 7 plus I root 11 over 2, you're going to get like a negative number. And then you're going to get more negative, and then you're going to add 15 to it to get to 0. So that's it. I think that is a worthwhile exercise. Let's finish this video out with this last page, though. Just a few more facts about complex numbers that are going to be useful to us. The complex plane, we've talked about this already. It has a real axis and an imaginary axis, horizontal, vertical, respectively. The complex plane, the complex number a plus bi is graphed as an ordered pair. A plus B, A comma B. But here we go. The magnitude of a complex number is its distance from the origin in the complex plane. In other words, Pythagorean theorem.
Mm-hmm.
How do you think Pythagoras would feel about complex numbers?
Nah.
He really didn't like irrational numbers, right?
I guess so. But it's
Wasn't that
also
the
like
thing
so far beyond what kind of maths
they did back then.
Right?
Yeah.
Like it's like, oh, how would you feel about cell phones? Like, I don't know.
We need a Bill and Ted Excellent Adventure 4 where they go back and talk to Pythagoras. He should have been a part of that movie.
There were more than one.
There's been 3 Bill and Ted movies.
That's insane.
One of them came out last year.
Oh my God.
I own it on Amazon.
I see.
I'm a big fan of Bill and Ted. I'm a big Keanu Reeves fan. I think we already established that.
Because that's your sourdough starter. Right?
That's my sourdough starter's name. It's also my favorite actor. Let's proceed. That's a good icebreaker. Who's your favorite actor? Let's talk about that later. Okay. What is the magnitude of this number? 6 minus 2i. You've graphed it. Thank you.
And then the magnitude is just what, like rooting stuff, right? Where you have like 6 squared and -2 squared.
So we got 36 plus 4, which is 40, root 40.
And that's like a thing, right?
Mhm.
2 times.
Yeah, take out 2 times root 10. Before we move on to B, quick exercise. What is its angle with the positive x-axis?
The angle with the positive x-axis.
Do you see what I've just drawn there before it?
Mhm.
Boom. What is its angle with the positive x-axis?
Would it be, oh, we can use trig.
Yeah. This is a great segue to next lesson, which is why I wanted to do it.
Cool.
Yeah, let's use trig. I'm going to call this angle theta.
That is what, -2 over 2 root 10, and then like arc sine of that.
What if I didn't have the magnitude?
Oh, then you can just use the a and the b.
Yeah, let's just do the a and b. So we got -2 and 6.
Arctan.
Arctan, yeah.
Which is what, like -1/3?
What does this look like, by the way?
It looks familiar. It's like translating between a rectangular and a polar coordinate.
Yeah.
Didn't
We're
we-
translating from rectangular to polar in a way.
Wow,
interpreting
nothing is new.
Nothing is new under the sun, is what my mom always used to tell me growing up. -3.21 radians. Let me, that's actually not, it's -0.322 radians. I've been writing a rattle out lately just so that everyone knows I'm not saying degrees. Technically, I shouldn't have to write rad, but I think it's appropriate sometimes.
And it's also super rad.
We've been toggling back and forth between radians and degrees now for a month or two, so I think it's valid. All right, so the reason why I wanted to find that angle theta is because I just wanted to reiterate the function of this number. Right? It is a number, and you can think about it in many different ways. But geometrically, what multiplying by 3 minus 2i does to any number in the complex plane is it dilates it to root 10, and it rotates it -0.322 radians. So if I have like some random number over here, multiplying whatever that number I just drew, which is specifically like 3.5 comma 6, -3.5 comma 6i plus 6i. Multiplying it by 6 minus 2i is going to rotate it this much and then dilate it by whatever that number is. If we did out the FOIL, we would get that number way up there. So having that angle is a convenient thing. And also it's going to segue to next lesson very nicely. Z equals 5i.
I graphed it already.
Nice.
And then isn't Z, the magnitude of Z, like wicked easy? It's just like root 25, which is 5 squared, which is just 5.
Boom.
Right?
Wicked
It's
easy.
like the distance from
Yeah, we could just straight up count it.
Yeah.
We're back in full circle. We're back in first grade. We're just counting up instead of to the right. Not that much harder. And it's our angle. What is 90 degrees? 90 Neil deGrasse Tyson's.
Pi
over 2. Whew. All right, let's close this one out.
Thingy things.
Thingy things.
Got the Z in there.
Yeah, the Z in there for you. There
What's
you have
your favorite
it.
coordinate system, Mr. Kirk?
My favorite coordinate system? Spherical, just to be different.
I actually really don't like spherical because
Yeah, neither do I. I'm lying.
it's
I
very
just wanted to be different.
confusing to have like multiple angles involved.
Yeah. It's like the distance from the pole, but it's in 3D, so you got to like rotate in the XY plane and like I guess the XZ plane. I don't even know.
Like I think it only makes sense if you had to like do the rabbit ear thing when you were a kid to get the TV.
I still do it, actually, believe it or not. I have DTV, and when I want to watch like a football game, I put on NBC and I rabbit ears, and I got to move the rabbit ears all the way to like the other near my window because I'm in an apartment with lots of brick walls, and I got to like. So you know what? Spherical is my favorite.
All right. Right.
Because of Sports. How about you? What's your favorite coordinate system?
I'm a fan of rectangular because it is a nice like way to translate between other things. Like I think it's just like and it's also very translatable. Like it makes a lot of sense when you're thinking about like navigation and stuff, which I still sometimes struggle with.
Yeah. Have you ever heard of Taxicab Geometry?
I recently heard about that, yeah, but I don't really I don't know. Like I feel like it's gonna get a rebrand, like Uber or something.
An Uber geometry? I love that. So Taxicab Geometry defines distances as like, it's like you're in a
your screen.
Oh, I'm not sharing my screen. We'll close this one out, guys, I promise, right after this. But like a taxicab geometry is we define distances not as the shortest distance between two objects, but the perpendicular distance between. So like if you're in a taxi cab and you need to get from point A to point B in a city, it's on a grid. So like it doesn't matter how you get there. All these distances are the same. So the distance in a taxicab metric is what we call it. So that's your keyword there, taxicab metric. Go ahead and look that up for a journal entry. The distance between these 2 points I've drawn, 1, 2, 3, 4, 5, 6, 7, 8, 9. No matter how you do it, 1, 2, 3, 4, 5, 6, 7, 8, 9. No matter how you do it.
Unless you're a bad taxi driver and you like go around.
Yeah, but that's just making a little bit more money. You're in the taxi cab for 5 minutes, not 4 minutes. Cough it up. All right, let's close this one out.
Yep.